So we would like, yes, you record my talk, I understand. Yeah. And the second problem is that usually reality, well, doesn't wait for your optimization. So it changes while the optimization is running. This is less of an issue if your optimization algorithm is super, super fast. Usually this causes your solution to be somewhat out of date the second that you emit it. So this causes us to create optimization problems that are no longer static, but dynamic optimization problems. And Vladimir Slanovov already presented you a small analysis about the volume of literature on dynamic optimization problems, which is, to be fair, frustratingly low compared to how much effort is invested into static optimization, especially considering that essentially most of real-world optimization problems are on some level dynamic. Yeah, if you recognize your problem as dynamic, you can do some fancy things like adapt and tune your optimization algorithm while you update your optimization problem. And you maybe even introduce some measures of stability or robustness, considering that maybe it's not suitable to get the last 5% of optimization potential out of the current state of the problem, when probably it will no longer be valid at the time your solution has translated into a decision and is starting to influence the system. And we have seen already in the talks before that usually when you apply black box optimization in form of evolutionary computation for dynamic optimization problems, you use some form of multi-population, partial population approach. But this is maybe not the whole answer, because overall mass of literature on dynamic problems is still way too low. So in short, many real-world applications still run with the iterative static optimization cycle, where you feed data into an optimization run, you let it finish, you make a decision, you feed data into an optimization run, you let it finish, you make a decision. What you should do, what I believe everyone should do if their problem is dynamic, is some form of initialization step, then create an ongoing, essentially open-ended optimization run, which constantly uses changes to update its own model about reality and emits decision when it deems necessary. Looks easy? I assure you very much it is not. Here, two short pictures about why we actually care so much about dynamic optimization problems. For the rest of this talk/tutorial, I will mainly deal with stacking operations, which is mostly because this is a type of dynamic problem that translates very neatly between the academic and the real world as much as possible. We will see later when this is not the case. You see on the left-hand side, stacking of large steel slabs. And on the right side, when these steel slabs are essentially rolled into coils and then put in a warehouse. This is something where you can very neatly tie optimization algorithm times to crane movements to have an interesting problem, both from a real world and an academic view. Dynamic optimization problems in this form, in comparison to the academic dynamic optimization problems like the generalized moving peaks, bring with themselves a good number of challenges. we have seen the mathematical formulation of a function being dependent both on the solution vector and the time point. Well, sadly, this function f is not told to us by the dynamic optimization problem. If you want to solve the dirty DOPs, you actually have to find or tune or learn your objective function very much by yourself, which is actually a massive undertaking. For many dynamic variations of static optimization problems, you can estimate, and it makes a lot of sense, that the solution for the static optimization problem is correlated to the overall performance in the dynamic environment. It is intuitive, and in many cases it will make sense, but it is actually just pure speculation. And assuming you have only the real world process where you cannot turn back time, it is very, very difficult to prove that the static optimization goal and the dynamic performance are in any way, shape, or form correlated. Then, of course, you have to deal with all the information kerfuffle in dynamic systems, like some information might be uncertain, some information might be missing at all. You have to do actually a lot of work to keep your real world process, the process that translates the solution into actual decisions, and the optimization process, to keep all those synchronized. You will have to invest some form of work. And then there is the problem of real-time coupling. That is actually, I want to elaborate on that. Usually for many academic scenarios, you define the computational budget that your algorithm has in a form of, well, number of evaluations. When your optimization process is inherently tied to the real world and the real clock, you will get some very interesting effects, like sequentially evaluating 1,000 solutions is very, very much more expensive than evaluating 1,000 solutions in parallel, because usually you have a decently sized parallel computing infrastructure. And the second thing is that your optimization budget now becomes part of your solution, because in some points in time, it might be advantageous for you to just not emit the new best found solution and just give the algorithm another minute, another 2 minutes to find a suitable, good solution, in this time a crane schedule, before you start actual operations. So algorithm runtime and algorithm evaluation budget now becomes part of your solution vector, which has its own intricate implications. Then, of course, your solution might be good for right now, and then you have 2 or 3 changes and the solution becomes very, well, unstable or unfeasible, or loses a lot of its original potential. And lastly, and this is the point that I will like to talk about today, is if you deal with all these challenges, the question of which algorithm actually works best is by far not a simple one, because you have the worst case of any time performance comparison that you can actually have. So full honesty, my talk is called benchmarking and not solving, for a very good reason. I will not present you solutions to all these problems today. The only thing I can show you today is a simplified version of this real-world problem where you can test your algorithms against. I cannot tell you what the best algorithm for these problems are. I can point you in a few interesting solution approaches, but as it is right now, and as I understand the state of the art is, there is no, well, current state-of-the-art algorithm to solve the dirty dynamic optimization problems. So let's go into the more domain specific parts about using cranes to operate the warehouse dynamically. And in the simplest of all formulations, you essentially have, a glorified pipeline. You have, at some point in the warehouse, you have an arrival area when you, in this case, we just call them blocks, or where these new blocks arrive, and you have some form of output area where you will have to move your blocks under certain conditions so that they can leave the warehouse again. And in between, you have buffer area, buffer stacks where you allocate your blocks in the meantime. Usually, you do this with a crane that takes a certain amount of time to pull up or drop down a block and to move along the crane runway. And in one of the scenarios that I'm presenting you today, these blocks are annotated with both a due date. This is the last point in time where you have to output the block until then, otherwise you incur penalties. Also, you cannot emit a block on the handover or output area whenever you like. You have to wait until they are ready, and you have to wait until the handover process is ready, because usually when you move large steel slabs out of a warehouse, you cannot just output block after block after block. You actually need to have people there and trucks there to remove the blocks that you no longer want to have in your warehouse as fast as they possibly can, which is, of course, not infinitely fast. This is the easy formulation, and now I can switch you to the slightly more difficult formulation, which is essentially in many modern warehouses that operate any form of cranes, you usually have more of them. And one of our company partners actually uses 5 cranes in their stacking operations. For the scenarios we will be looking at today, we only use 2, and believe me, 2 cranes are enough to make the problem significantly harder. Also, you can have more or fewer arrival and output areas. Some scenarios even give you additional information like, okay, here is a rough estimation when the next arrivals will appear. Be aware, these times may not be completely accurate. Your optimization algorithms most certainly will need to have some form of machine learning component to estimate all forms of errors and times and speeds. In this scenario, we also see the violet and blue coloring, which corresponds to the different output areas. Well, obviously, you would need to move the blue blocks to the blue output area and the violet blocks to the violet output area. So this is essentially a small domain model of a real-world dynamic stacking operation. You will see that most of the challenges I've talked before can be adequately captured with this model without introducing more of the, let's say, real-world baggage, like okay, how to interface with an actual production system and human worker times and other more complicated constraints that you will probably have to deal with when you try to move your algorithms to a real-world application. The next question is, when we have our domain model on which we want to perform optimization, we will need some form of agreement on how we actually measure the performance. First of all, we do not want to block these arrival areas. Of course, every area has some form of maximum height, We cannot put infinitely many stacks there, because at some point you will simply hit either the ceiling of the warehouse or an area where you block movement of the crane. So there is an absolute limit to that. And you do not want to block the arrival time, because then the arrival stack, because then processes that create these blocks, like let's say a casting oven, you will need to stop those, and then a lot of people will be very, very angry with you. Second criteria you could possibly imagine would be, well, the number of total blocks delivered on time. In the interest of energy savings, you will probably want to minimize either the number of crane moves or the distance that the cranes need to travel. Of course, you want to minimize your due date violations. And in case of the second scenario, where you have to match the colors, well, at some point you probably will be in a situation where you absolutely have to violate the color orientation. So keep those at a minimum, but maybe there are other objectives that simply supersede this this pre-assignment. And also you can create a big number of matrices. To be fair, the problem is both multi-objective and not multi-objective. In many cases, the first thing you will need to do is not find an algorithm that outperforms another algorithm in any of these 5 performance metrics. The first, and frankly pretty difficult level of this game, is to find any form of algorithm that does not reach a completely infeasible warehouse state where no longer any meaningful moves are possible. So if you have a running algorithm, I would say you can be pretty proud of yourself, and then you can do the fine tuning in some form of multi-objective fashion. But usually don't be fooled by these larger number of optimization criteria. You will not be dealing with crowding distances and hyper volume contributions for your algorithms for a long time. Since we're talking about solvers, this is pretty much everything that I can tell you about the solvers that we have fielded against these problems. Essentially, 2 general approaches, which is first a rule-based solver that simply uses a number of handcrafted and or learned rules to decide which crane moves have priority at any given point in time, and that only emits the next matching move whenever a crane is ready. And the second is a more involved way, where we mapped a dynamic warehouse operation problem to a static block relocation problem. We solved the block relocation problem using a branch and bound algorithm. You could also solve it via a meta heuristic, like a genetic algorithm. And well, the next crane moves are then determined by the solution we have developed with the branch and bound variation. On that note, we can usually solve with branch and bound the abstracted warehouse scenarios that I'm presenting you here. In the real world, the warehouse on the right side has I think over 1,000 individual buffer areas. To my knowledge, there is no branch and bound algorithm that would ever finish on this scenario. So here you actually have to use the meta heuristic. But for the smaller abstracted variations of the dynamic stacking operation, you can actually use exact solvers to a actually pretty satisfying degree of performance. Yeah, here a small comparison of the two approaches that was published in a paper a few months ago. And here we see actually a pretty easy comparison between both algorithms, because at some points the lines simply diverge and one of these algorithms constantly outperforms the other, except for handover utilization. Here we see the overall problem that you can have, that some algorithm might outperform another algorithm for a certain amount of time, but not forever. And the only actual performance measure that would really interest you is the forever performance, which is, of course, the one performance that you can never actually measure. So there are some shades in there. Next thing is we present not only the model, but also the benchmark instances for these dynamic stacking operations. These have actually a good number of parameters, and it is very, very easy to make either a scenario that is so simple that you don't need any form of optimization, or a scenario that is so hard that no optimization algorithm ever could perform even adequately in any way, shape, or form. So we are currently using queuing theory to estimate all of these parameters. And if you want to create your own dynamic optimization problems that is in some form building up or losing a state, I would urge you to do it yourself, to find a queuing theory or another theory that roughly describes your problem and not just eyeball all these numbers, because you will find that that the parameter space for problems that are actually interesting to solve is extremely narrow. Yeah. This slide is mainly for documentation purposes. We provide you with benchmark instances of varying size, both in buffer stacks and in arriver and remover speeds and utilization. Yes, you don't need to implement everything yourself. We are hosting a yearly competition on these problems, and you're all very welcome and invited to participate. We will look at the website live in a second. If you don't want to participate and think, I don't care what the guys in Upper Austria are doing, you can simply just take our code and maybe move from a dynamic stacking operation to any other dynamic optimization problem that you want using our software architecture. Speaking of software architecture, static optimization problems are usually defined by some form of problem interface. Solution goes in, quality goes out. The type of dynamic optimization problem I'm talking about now is substantially more intricate when it comes to software engineering, because what you're essentially doing when you want to have both a visualization and the form of real-world coupling, you need to create some form of message passing middleware that communicates both with your client that solves the optimization, that builds and solves the optimization problem and emits suggested decision, and the dynamic simulation, on the other hand, that receives and sends messages about the decisions that you want the simulation to perform and the overall world state. If you're really fancy, you can program yourself a front end to have a visual representation of the of what's going on in the simulation. Yes. I think we can go to the more practical part of my talk. Under dunstack.adapt.at, you will find our competition website, which is running all year, even if the competition is not running, and you can test your algorithms against our problems anytime. You're very welcome to. And for now, I would like to create myself a small stacking problem, 3 buffer stacks, smallest utilization, and then try to create a small algorithm that at least does something with you. I'm not going to program everything concerning the software architecture and the message passing myself. We provide a C#, C++, Rust, and Python starter kit. I will be using the C# starter kit for the purposes of this demonstration, simply because it's the language that I am myself most familiar with. You can clone pretty much everything from the GitHub repository, but for obvious reasons and brevity, I have already done that. Under Dunstack starter kits, I will use the C# variation, and I have already started that one in Visual Studio. The message parsing code is already presented to you, and let's go down to the nitty-gritty details with you, because I would like to create a very, very simplistic and even, one could say, dumb rule-based optimizer with you. We have essentially a main loop retrieving and sending messages, and a planner object with a plan moves method that requires us to emit, well, our decisions, our moves that we would like to send to the crane for it to perform. And the first I would like to do with you is, well, if the handover is ready, we will need to move some block towards the handover stack. So let's ask if the handover is ready. If that is not the case, we don't need to care about this rule. If the handover is ready, let's find ourselves the top blocks in the warehouse. We achieve that by asking all the buffer stacks in the world where they are not empty. Then we select ourselves both the block and the corresponding stack. We can only use ready blocks, and then we save ourselves all the potential candidates that we could move to the handover area in an array. I hope it is okay with you that from an intuitive point of view, I would like to move the block with the lowest due date to the handover first, because if possible, I do not want to incur due date violation penalties. So I order my blocks by due date. I create for every block a new crane move. Where we need to define the block ID, the source position ID, which is essentially just the number of the stack, and the target ID. Target ID is always the handover. And now let's add all these moves that we've created to the current schedule. And when we are asked to make our heuristic schedule in the plan move methods, I will just add any possible move to the handover that is available to us. If the handover is ready, I would just add that to the current schedule. You need to parameterize your program with the running simulation, because you're sending essentially everything to our servers at the University of Applied Sciences. So where is my web page? The experiment section, where you can look on upon your own started and finished and currently not running experiments, shows you both the TCP endpoint, which I have already inserted as the first argument, and then requires you a GUI to specify with which simulation you essentially want to communicate. Let me just add that and then run our first dynamic optimizer. And quote this because it's, well, a very, very simplistic optimizer. So gods of compilation, be with me. Thank you. And now I can start the simulation and have a visualization of what is actually happening. We will need to wait until one block is ready, until we can see the effects of our scheduler. But at first, we see the first and probably best tool for benchmarking dynamic optimization algorithms, visual inspection. I think you can all agree with me. Well, we have blocks arriving on the arrival stack. We should probably do something about this. It is very, very, very hard to solve dynamic optimization problems without domain-specific inspection. There are papers about dynamic optimization problems with time linkage, like the ones we have here, where your solver makes decisions and has impacts on the next states. And they essentially usually come to the conclusion that on general basis, we cannot solve these things. Right now, we have accrued already due date violations because our rule only considers the topmost block of each stack. And since the stacks didn't spawn in an ordered fashion, we failed to dig out block number 11 here. Since all of these scenarios are pretty much random, I am sorry for the wait time. I hope that block B4 will reach a ready state sooner rather than later. Nonetheless, this is essentially our very first, our program sent the required solution to the schedule, and we moved our first block to the handover stack. I was incurring an exception later because I did not care about sequencing all our schedule entries correctly. But nonetheless, this is a small demo. You can, of course, do other simulations like let's create a more complicated issue with 2 cranes in the rolling mill scenario. I will not create a solver for that one, only show you the visualization. Here we have 2 cranes, and at this point it is actually very important to not only specify the schedule in a working order, but also define the precedence constraints between moves that you create in order to tell the cranes whether they have to wait for other operations until they can start with their current move. Lastly, a few rule of thumbs that we have found from the competition for generating handcrafted priorities, which is like check if the block are ready, can the block put on the handover in time, or will you accrue due date violations anyway? How much time do you have until the due date runs out? Of course, it is always an interesting question, how many blocks are above which block in which stack, and does this change your priorities for which block you tackle first? For a more involved way, especially for the second crane problems, our best working algorithms separate the stacking problem from the crane scheduling problem, because those are essentially both 2 NP complete problems in their own right. We usually do stacking operation first, and after the stacking, our optimizer provides us with the potential moves that we can make. We use a scheduler that essentially solves a warped two agent traveling salesman problem to actually decide on the real final and exactly timed schedule for the simulation. I know I shouldn't talk about our conferences here. I just wanted to tell you one thing. This year we had 23 registered participants all over the world, and not a single one attempted to submit a scoring run for the 2 crane problem, which should give you a small estimation on how the community perceives the difficulty of the 2 crane staking operation. And you can do the interpolation yourself on how difficult it probably is to solve a 5 or more crane structure where you have evasion cascades and you have to avoid train collisions and blocking yourselves out of moves. So lastly, if I have the time, I would like to show you something about the analysis of these problems, which is quite an interesting thing. You can track the performance of your algorithms without visually looking at them by doing essentially a machine learning trick. you can try to capture the current state of the warehouse and the current state of the algorithms by just throwing numeric features at them. Here I have created about 30 of them. You can differentiate between useful and non-useful features by simply using them to predict the short-term change in the objective that interests you, like let's say 2 minutes into the future, and then weigh all of these measures by variable impact. And then you can do visualizations of every measured warehouse state on the time axis and visualize them, for example, via t-distributed stochastic neighbor embedding. On the left side, we see the states of the warehouse for the one crane scenario, colored by the scenario ID I presented earlier, where we have different characteristics in terms of utilization, where we see you can separate these different scenarios very easily, and you have very, very distinct outer clusters, which is an artifact of the fact that the algorithm that was performing while I took these analysis measurements was performing quite better in terms of how the warehouse looks than the original initialization of the stacks. And on the right side, we see something very interesting. We see the embedding for the 2 crane scenario, and we have these longer, let's say, worm or snake-like structures. We can explain those when we introduce time dependency and transform all of our data points into transitional graphs and then plot them via spring layout. All of these snakes or worms are essentially states where the algorithm did not manage to perform adequately, locked itself into some form of state where no moves were no longer possible because all of the stacks were filled to the brim, and then the algorithm essentially stopped operation, which is somewhat depressing for me because it means that we are still a good way away from having open-ended prescriptive artificial intelligence that does all this range scheduling for us, because essentially you always need to have a human overlooking the open-ended optimization algorithm for, well, deteriorating states. And with that, I thank you for your time. I am both very open to questions and your contributions to this field, because I think we have way too little in terms of dynamic optimization.
Thank you very much, Bernhard, for your very impressive presentation. Dear colleagues, please, your answers. Sorry, your questions. Okay, I have one question, a little bit independent of the talk. Do you make the difference between non-stationary optimization problem and dynamic optimization problem?
To be fair, I'm not sure whether this is mathematically fully correct. I would say non-stationary optimization problem is one that changes completely independent from whatever the algorithm does, and you only have to track the optimum. And I would say really dynamic are those things that have the algorithm problem interaction, where whatever you do causes actual changes in the problem state. But I don't know whether this is mathematically all that correct.
Yeah, the dynamic behavior can be described, for example, at least theoretically, with differential equation. Non-stationary behavior originally cannot be described anyhow, and only
to
after some.
be fully fair, I don't know whether the very discrete stacking problem can be described by differential equation, but if I have to guess, I would probably say it can.
Yeah, non-stationary behavior means that, let me say, graph of function landscape can simply occasionally jump out of current position, not just slightly go accordingly to some maybe unknown law.
The arrival of a block in that case would be a jump. It would be a single discrete event, but I think you can very accurately, let's say, smooth it out with a differential equation. You can approximate such a jump, I think, fairly well. I am not sure whether there are differential equations for such a problem that is so discrete in nature, but I think the world of mathematics is vast and you could do something very unholy to actually create a differential equation approximation of the problem here.
Okay, I see. Thank you. Dear colleagues, any question, please?
Yes, I have a question.
Yeah, Ivan, please.
Thank you once again for this topic. It's very interesting according to industrial applications. So my first question is, am I understanding correctly that dynamic optimization problems and dynamical programming are different because in dynamic optimization, you don't know in advance the reaction of the system or what will happen in the system later?
That is a loaded question, to be fair. In this case, we don't know what happens in advance, but to be fair, you can learn it. You have enough domain knowledge that you can, I know for sure that you can learn with something like reinforcement learning, your own regret functions, and you can probably hard code some form of system response and then go into dynamic programming. This is something I should have mentioned within the talk, but these forms of dynamic optimization problems actually open the playing field for different strategies to compare. You can do reinforcement learning. You can do essentially everything with some form of neural network that just emit priorities. You can do dynamic programming. You can build yourself a domain model and apply a black box meta heuristic like we are doing. But at the end of the day, everything you do that takes messages and emits messages is essentially a possible candidate for the competition. So I am not sure whether I can define, well, this is dynamic programming and this is dynamic optimization. There is no clear boundary to that in any way, shape, or form. I'm sorry that I have to give such a cop-out answer, but
no, that's very good answer. Thanks. And you've already mentioned this link to a second question. Were there participants who used like reinforcement learning?
To my knowledge, none. I know of at least one that tried, but they didn't. Reinforcement learning always involves a lot of time, and for just a competition, people often say, I don't care. I think they didn't get it up to the point where they could compete with the handcrafted priority rules, and at some point they just said, okay, no matter, I have other things to do, which saddens me to an unbelievable degree.
Okay, and this DIN-stack framework, does it actually allow somebody to try this kind of approaches, or is it not very fitting to this reinforcement learning?
I think you very much can. you have to decide on a few things yourself, like what is your regret or loss function, or so. You would have to extract it yourself from the domain model, because the software we give you right now does not specify which of the objectives you should actually follow. You can do that however you want, but I think it's very much appropriate to use here.
Okay. Okay, thank you very much for your answers.
So can I ask answers?
Yes, sure.
Question, Alexander Garnov. What about relationship between your algorithms and algorithms from maximum Pantragen principle, maybe in discrete variant?
Sorry, I have a maximum what principle?
Maximum Pantragen principle.
I am sure I have to be fully honest. I don't know this class of algorithms. Maybe I know them under a different name. Maybe I haven't heard of them at all. So I cannot fairly answer the question. I would have to look that up first.
Thank you.
Pantragen is the name of person. Maximum principle in dynamic optimization is one of main approaches, at least it was.
Is it a black box optimization approach? Is it a...
No.
No,
Okay.
it's not.
Okay, here I have to fully admit, maybe I'm out of my water here, and I have not heard of this type of dynamic optimization approach.
Alexander Yurich, is it enough?
I don't know about principle Pantragen. I know more. Thank you.
Okay, thank you very much. Any other question, please?
I have one more, if it's possible. Can you share if there is a growing interest from the industries in this kind of problems? Or
I can only share what we see from the industry in Upper Austria. I don't have a literature review on that, but to be fair, yes. These problems inherently relate to the industry 4.0 trend, which is pretty, I would say, pretty substantial right now, because the most important thing that you can do with the also celebrated digital twin of your factory or system is essentially make decisions based on it. And all of those are in their core dynamic optimization problems with time linkage, aka problem algorithm interaction. So I would say they are supremely relevant from a real world point of view, but the literature on it is somewhat lacking, and the most prominent reason I would think about is because they are pretty difficult to implement from a software point of view. It's simply a lot of work. You can easily test a few hundred algorithms on a traveling salesman problem, but to create your own dynamic feedback loop with some form of real-time constraint things, that is actually a lot of work, and for many researchers, sadly, too much work for a paper.
okay, thanks.
Well, our time for this tutorial is out. Thank you very much